writing. 3, 4, 5. And I did not leave enough room for myself. Excuse me. Okay, so we got to do that 6 times. The problem with this is that we don't necessarily know how to do this, but we do know how to do small pieces of this. So I want you to ignore the back pieces and do the part that we know. We know how to do FOIL. So we're going to do that part first. Okay? We're just going to take this to the second step because it should give you a clear idea of where to go. So I'm going to ignore this. I'm going to just lay the calculator over top of it so you don't have to look at it. And I'm going to FOIL this. So x times x gives us x squared. X times y gives us x times y. We can't do anything there. And then here we get again x times y. I'm going to put those in alphabetical order so it's easy to tell they have the same last name. I'm going to go to the back sides. I'm going to get y squared. Okay, combine like terms. We have xy and xy. Those are the same, and the rest of these are all alone. So I'm going to carry them down. xy plus xy gives us 2 of those xy's plus the y squared. Okay, now I'm going to uncover one of my other pieces here. So it tells me to multiply by xy again. Using the commutative property, I can put that up front or in the back, wherever I feel most comfortable. Okay, so if you want to put it up front, that is a-okay by me. We're still going to use the concepts of FOIL. So you should have noticed if the x went to each piece of this and the y went to each piece of this, in order to do our next step, we just take our x, we go to each piece. So x times x squared is x to the third, just like we did yesterday. Then x times 2xy. Okay, remember this would be 2x times x, which is x squared, and then y. Okay, and put that one out, plus xy squared. Now I have to distribute the y. Same way, same form, go right underneath, we get x squared y. You should notice that that is the exact same last name as him. And then we get 2xyy, which is y squared. And then y times y squared, which is y to the third power. Okay, I'm going to stop here, and we're going to analyze what has the same last name. So, is there anything in common with x to the third? Any other last names that have x to the third? No, nada. So I'm just carrying it down. We're still talking here, guys. Don't be afraid. Next one, I have x squared y. It's important that you notice the squared because x and y aren't the same as x squared y. So I have x squared y. Do we have any other x squared y's? Yes, right over where? There it is. Okay, so I have a 2x squared y and a regular 1x squared y, which gives me 3 of those. 3x squared y. Same last name. Nothing changed there. Next, I'm going to circle these ones. I have xy squared. I see another xy squared. So I get 3 of those now. 3xy squared, like Lacey said. And then y cubed falls all on its own, so I'm going to put y cubed. Now I'm going to stop here and see if we can just do a little bit of review from yesterday. Is this in standard form? Lyle says yes. Was that a yes? Uh-huh. What is the degree of the first term? 3. What about the second term? Ooh.
6.
Okay, so let's redefine what degree means, right? It is the total number of exponents there are. So let's look at our variables. 2 and 1 make 3. So this one is of degree 3. This one's of degree 3. What about this one? 3. 2, and remember this one has that imaginary 1 that we don't actually see, but it's there. So it's 3 again. And then the last one, 3. So these are all of degree 3. Therefore, the polynomial is of degree 3. And it is in standard form because they're all of degree 3. So really, I could put these in any order, and it would still be in standard form. So it's pretty much whatever's most pleasing to your eye at this point. Now, if I was to continue this next step, I would just uncover my next xy and multiply again. Okay? We just keep doing that, combine like terms in between each one, and we would just keep those steps rolling. Okay? The example from the book just went to the third. So this is their example, and we're just going to stop there so that y'all guys can see if the next step needed to go to the 4th, then we would go ahead and do another xy. If we needed to go to the 5th, we would go ahead and do another xy. And then the 6th would be that last xy that I barely fit on the page. Questions there? Okay. There is a rule on exponents that we need to re-go over and make sure that we still understand. Anything to the 0 power is equal to what? Does anybody remember? 1? I heard it. Okay. I want to verify that we understand why. So if I had, let's say, x to the 3rd, okay, and it was over x to the 3rd. When I divide things with like bases, what do I do with their exponents? Okay, when multiplying things with like bases, we add their exponents. So what do we do when we divide them? We subtract, right? So we have x to the 3rd minus 3, because we're subtracting these two exponents. So really, we get x to the 0, right? Because 3 minus 3 is, of course, 0. And then the answer to that would be just 1. Now, I want to analyze why this is true. I'm going to put a real number in here. Ready? 3 to the 3rd. 3 to the 3rd is what? 27, right? What if I had 3 to the 3rd over 3 to the 3rd? That would be the same as 27 over 27, which is exactly what Lyle said, 1, right? So this is why anything to the 0 power is 1. Because in reality, it's telling you if you're really y to the 0 power, that's the same as y over y, which is equal to 1. Okay? So there's y. So if you see something that is to the 0 power, you can immediately pretty much mark it out like that and put 1 in its place. Okay? Like a direct substitution almost. Alright, there's a triangle on here, and I want you guys all to zoom in on it. So open it up big like this on your iPad. Zoom in on it. It's called Pascal's triangle. We're going to start copying the first 3 rows. So copy the first, well, I guess it's technically the first 2 rows, because the first row is technically row 0. So at the top, put 1, and then out to the slight left and slight right, we're going to put another set of 1s. And then we're going to do 1, 2, 1. And this pattern of 1s is going to continue outwards the whole time. So 1, 1, 1, 1, like that. We're going to continue on. Now this is row 0. This is row 1. And obviously that pattern continues on down the line. So row 3, row 4. Now I want to see if we can analyze what's happening. So if we go down to the next one, we'd see 3s appearing in the gaps. We want to see if there's a pattern. Can we analyze this pattern and figure out how to get from one to the next? So here we see 1s, 1s, and then we see a 2 appear in the middle, and then we see a 3 appear in the middle. If I was to guess, I'd say there's going to be 4s popping in here somewhere, right? But why? So she's saying we would just add 1 to that number. So, okay, maybe that's a possibility, but where does the 6 come from then? The 2 3s. Oh. So maybe she's right. Let's see. She says the 2 3s would add up to give you the 6. Well, look at this. 3 and 1 add up to make 4. 3 and 1 add up to make 4. 1 and 1 add up to make 2. Are we starting to see a pattern? If the 1s continue on the outside, and we move on down to row 5, which is not pictured there, can we predict what's going to go in between? What would be right here? 5. Why, Hannah? Because 1 and 4 make 5, right? What about right here? 10. And here? 10. And here? 5. Okay, so this triangle would continue all the way down. Now, it's not just important for us to know that we can make this triangle. We also need a name for it. It's called Pascal's triangle. P-A-S-C-A-L apostrophe S. But we also need to know what it's used for. So there's a pattern to this, to say the least. The coefficients of the terms also follow a pattern. The first 5 rows of the Pascal triangle are what we just created. So if we go back and we look at what we did here, these numbers, we should have created something with the Pascal's triangle. So look at row 3. It's this one right here. Okay, everybody should be looking at row 3. And we want to look at what we got for an answer, which is right here. Okay, so I'm looking at row 3. If I multiply the same thing by itself that many times, we'll start recognizing a pattern. But look, the coefficient of the first term is 1. See if I can get that all in one picture here. The coefficient of the first term is 1. Second term, 3. Third term, 3. Last term, 1. Kind of interesting to see. So if I would have multiplied this out 4 times, you would have noticed a pattern of coefficients that would have followed this. 1, 4, 6, 4, 1. So Pascal's triangle is actually creating a shorthand version of ways to multiply binomials multiple different times for each row. Okay? Why does it do that? That is a very long explanation. If you are still curious after notes, I will explain it to you. Alright, so if we use these, we can hopefully help ourselves do some shorthand math here. So let's see what happens if we would have done this same problem. We're going to try to use Pascal's triangle here a little bit. If we would have done, say, x minus y instead of x plus y, which is what we did last time, to the third. Okay? I want to see if we can predict the answer. Now, using Pascal's triangle, to the power of 3, we're on row 3. Okay, so I'm just going to write in the coefficients real quick. 1, I'm going to put big spaces. 3, 3, 1. That should be my pattern. Alright? So here's the kind of neat forward-backwards trick that we're going to use to find out what our variables and exponents will be. The front will always be the first thing that you see in your binomial. The back will always be the back thing that you see in your binomial, on a binomial expression. Paul, can you pick your head up so I know that you're looking at that screen and not laying down? Okay, and we'll start right here at exponents of 3 because it was going to be to the third power. Now for every one decreasing this way, I'm going to go down an order here. Okay, and on the next one it's just going to be x. And the last one would be x to the 0, but we don't need to write that because we already know that x to the 0 is 1. Okay? And from this side, since I have y to the third, it would go down 1 order of magnitude each time. So it goes 3, 2, 1, none. And same way on the other side. Now here's the difference between the minuses and the pluses. You're going to have to find the pattern. Okay? If this is a positive number, then all of these are going to be positive. Okay? If this is plus, then all of these are going to be plus. If this is minus, you're going to alternate pluses and minuses. So ready? Minus, plus, minus. So we can use Pascal's triangle to shorthand a lot of this stuff. So, tell me, would you rather use Pascal's triangle or do this? I'd probably rather use it. You got to understand why, but I'd much rather use Pascal's triangle than try to do this. So let's write down some rules. First, we're going to deal with the binomial that is positive. Okay? So there's a binomial that's positive. Step 1. Use, I guess he deserves a capital letter, Pascal's triangle. For coefficients. Okay, so that's step 1. That's going to be step 1 when we're doing negatives as well. But we have to use Pascal's triangle for identifying our coefficients. Step 2. We need to figure out what pattern our operators are going to be in. Okay, so well, I guess that would be step 3. Step 2, we need to go in descending orders of magnitude with our variables. Okay, so establish variable exponents. Okay, you know you're going to have 2 variables because they are in the original binomial. You just need to establish their order. So it goes 3, 2, 1, nothing. And then on the other side it goes 3, 2, 1, nothing. Okay. Third one. Now we need to decide our operators. So decide operators. A subnote here. If it's positive, they are all positive. If you don't remember, positive and plus signs are exactly the same. Okay? So if they are positive, then they are all plus signs. The second part of that subnote is if it has a negative, then you alternate. Whoops, we need a then in here. Then alternate signs starting with minus. Alright, that example is very important to you so you'll understand how to do it. If you don't have that example in there, this is going to be a much harder problem. I guess originally I was just going to do it for plus and minus, but I turned it all into one nice little chart there. So I guess you can take out your plus that I wrote next to the binomial. Okay, give y'all a second to catch up. If you are caught up, we can go ahead and flip to the next page. That's where we're headed. If my computer will let me. There we go. And we'll do one more example, and we're going to do kind of a big one just so that we can see it and how it works. We're actually going to do it as groups. So when we do this as groups, Nick, I want you to jump over here with Lacey, and Trayton, I want you to go with Paul's group. Okay? So here's your example. It is going to be a minus problem. Okay, it's x minus y to the fifth. Now we've already established our fifth row of Pascal's triangle. So use that fifth row to solve that problem. X minus y to the fifth. Okay, follow those steps, please. Permanent down, you should have your Pascal's triangle. Step 1 says to do what? Step 1, from your finger, just go down. Use Pascal's triangle to establish coefficients. Let's establish them down. Good. So establish your coefficients using Pascal's triangle. Should be something to the effect of 1, 6. 1, 5, 10, 10, 5, 1.
No, sorry, I was on it.
Your coefficients are numbers. Remember, coefficients are numbers. Coefficients are numbers. Variables are those letters.
What would actually find the
Establishing the coefficients. That's what this is.
No. I'm out of high school. And if it was,
It's okay, that's our general answer call. I'll tell you when you
they don't need stiff lines or
I'll tell you that you're getting which of those balls.
No.
If you wish. But, unless you have general curiosity. Wow, you need to write down.
Why would that be a curiosity?
Coefficients. Okay, second step, it says that you need to start establishing your variables and their order, right?
Looks like X.
X is 0 is 1, right? So it's 1 times 1.
Okay, I hear Hannah doing some explanation over there, and I hear a lot of grumbling because they don't want to do it. But I want y'all guys to know that this is the easy way. You can do it the hard way. There is a much longer hard way. Okay, if you're just starting, if y'all are just starting or you didn't understand, eyes up on the board. Okay, eyes up on the board. Pascal's bottom row of triangle, which was the 5 for us, said 1, 5, 10, 10, 5, and 1. Okay, so the first one was establish your coefficients, which we've done. 1, 5, 10, 10, 5, 1. There they are. Then your first x goes right here, x to the 5th. And then you're going to go and decrease it the whole way down. X to the 4th, x to the 3rd, x squared, x, and then no x's. You literally just go 5, 4, 3, 2, 1, which I have a full, I just believe y'all guys can count down. Then on the right hand side, because that's where my y is, I'm going to start again at 5. I'm going to go 4. I'm going to go 3. I'm going to go 2. I'm going to go 1. And then none. And I'm done with that part. Then the very last step says that I need to decide my operators. If it has a negative, which it does, then I alternate signs starting with the negative. So minus, plus, minus, plus, minus. That's it. This is literally writing down a pattern. This is very little to do with math, unfortunate. This is a shorthand way to do long math problems, because I guarantee you, you would have took up an entire page trying to solve this the right, long way. Pascal's triangle does the math part of it for you. Okay, here's your final examples. Here's the problem. The problem is 2x plus 3 in parentheses. Okay, it's still binomial, but this one's to the 4th power. Now, we're going to solve this the same way using Pascal's triangle. And we're going to use row 4. So, if you recall on your notes, row 4 was 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. So, we're going to use those to hopefully solve this. Okay? So, the part where we kind of get confused is the 2x, because it's got now, your x has a coefficient. So, I'm going to go ahead and write down that bottom row, 1, 4, 6, 4, 1. Okay, so those would be our coefficients. So the first one you'd be looking at would be 2x. Okay, I'm going to put that in parentheses, and it's going to be to the 4th power. Okay, so it's actually x to the 4th as well as 2 to the 4th. Okay, so that's where a lot of people get confused. And I don't want you to get confused by that little thing. Okay, so if I use my Pascal's triangle, I'm going to spread these out real big. 1, 4, 6, 4, 1. My first one is going to get a 2x to the 4th. My next one is going to get a 2x to the 3rd. The next one is going to give me a 2x squared. The last one's going to be 2x1, and then no 2x's at all. And then nothing on the last one. Okay? And then if I start at the back, because this was a 3, okay, when I'm starting at the back, it's going to be the same kind of concept. I'm going to have 3 to the 4th power, and then I'm going to have 3 to the 3rd, 3 squared, 3 to the 1st, and then no 3 at all. And because this was a positive here, I'm going to put pluses in between each one of these. And I'm going to use the same concept. So 4 goes here and to here. So this becomes 1 multiplied by 2 to the 4th, which is 16, x to the 4th, plus, I'm going to do this next one, 2 to the 3rd is 8, 8 times 4 is 32, 32 times 3 is 96, 96, and then we have x to the 3rd, x to the 3rd. Next one, we end up with 4 on that one, x squared, so it's going to end up with an x squared at the end, and a 9. So I'm going to write this in 4, I'm going to write that in 9, so I get 6 times 4 times 9. I don't know that one off the top of my head. I think it's 216. 6 times 4 is 36 times 9, yeah, 216. 216x squared. This one here, 3 to the 3rd is 27, so I have 2 times 4, which is 8. 8 times 27 is going to give me that same thing, 216. So plus 216x. And then the last one, 3 to the 4th, is 81.